First, listening. As electric current is conducted through a material, any opposition to that flow of electrons, resistance, can result in a dissipation of energy, usually in the form of heat. If the amount of heat generated is sufficient, living tissue may be burnt. The effect is physiologically the same as damage caused by an open flame or other high-temperature source of heat, except that electricity can burn tissue well beneath the skin of a victim, even burning internal organs. Electric current can affect the nervous system. It may override the tiny electrical impulses normally generated by the neurons, overloading the nervous system and preventing both reflex and volitional signals from being able to actuate muscles. Muscles triggered by an external shock current will involuntarily contract, and there's nothing the victim can do about it. If the conductor delivering current to the victim can face the palm of his or her hand, the hand must grasp the wire firmly because of the clenching action force. The victim can't let go of the wire. Medically, this condition of involuntary muscle contraction is called tetanus. Electricians familiar with this effect of electric shock often refer to an immobilized victim of electric shock as being froze on the circuit. You should interrupt the current through the victim so that shock-induced tetanus may stop. Even currents too low to induce tetanus can scramble nerve cell signals enough that the heart can't beat properly, sending the heart into a condition known as fibrillation. A fibrillating heart flutters rather than beats. How AC can affect the body depends largely on frequency. Low frequency, 50 to 60 Hz, AC is used in US 60 Hz and European 50 Hz households. It might be more dangerous than high-frequency AC and is 3 to 5 times more dangerous than DC of the same voltage and amperage. Low-frequency AC can produce extended muscle contraction, tetany, which may freeze the hand to the current source, prolonging exposure. DC might cause a single convulsive contraction, which often forces the victim away from the current source, MMOM. AC's alternating nature may throw the heart's pacemaker neurons into a condition of fibrillation, whereas DC might just make the heart stand still. Once the shock current is halted, a frozen heart has a better chance of regaining a normal beat pattern than a fibrillating heart. This is why defibrillating equipment used by emergency medics works. The jolt of current supplied by the defibrillator unit is DC, which halts fibrillation and gives the heart a chance to recover. In either case, electric currents high enough to cause involuntary muscle action are dangerous and must be avoided at all costs.